Bio 181, Chapter 5 on cell membranes, and we're looking at transport. So in this key concept, we're focusing on passive transport. This is going to be in contrast to active transport, which we'll cover later. So in passive transport, there are two types of passive transport. So I'm going to just write it here. This is a big misconception. So passive transport, the first one people always get, okay, it includes simple diffusion. But the second one, because of the name, I think it confuses people. So the second component is called facilitated diffusion. And even though it's facilitated, it's still passive, which means it doesn't take any energy in the form of ATP to complete it. So both of these, no ATP is required. And that molecule is the energy molecule of the cell. So this is chemical energy molecule. So there's no extra energy that has to be added for this type of transport. So in simple diffusion, the type of molecules that go through in simple diffusion are going to include small nonpolar molecules, right? So they're small and they're nonpolar, so they're not charged and they don't have any charge imbalance, right? They're not polar, they're not completely charged. In facilitated diffusion, now these atoms can be larger, okay? So, and they can also be charged. So they can be larger, they may be, but they may be any one of these characteristics. They may be large, they may be polar, and they may be charged. So let me give you a few examples. So simple diffusion example here, we already talked about this in a previous video, but that would be oxygen gas or carbon dioxide or a steroid like estrogen, which is a lipid. That can go straight through. If it's facilitated, now these can be a molecule like a larger molecule like glucose, if there's a large concentration outside the cell, which is also polar. Charged often are going to be ions. So ions are going to require facilitated diffusion. So it moves substances down their concentration gradient, which means that facilitated diffusion is only going to move substances in the direction. Let me do a ion here. So I've got sodium ions out here. Got a whole bunch of these. It's only going to move them from an area of high concentration. Say there's only one in here. It's only going to move them in here, this direction. And because it's facilitated diffusion is going to require a protein. So it can't go straight through. It's going to require a protein transport, right? Protein transport. And that's because this molecule is charged. It cannot go through the hydrophobic cell membrane. So anything that is charged, anything that's polar, anything that's large is going to, can go in through a membrane with the protein carrier, but it's only going to go in the direction of high concentration to low. Now, say we have another scenario, same cell, but later on. So say the same cell later on you've built up a whole bunch of sodium inside. Okay. So now you've got tons of sodium in here. Okay. Now, if you open this protein carrier, it's going to go out. Okay. So it's always going to go in the direction from high to the direction of low. So in this case, this is high now inside. That's a little confusing. I'm just going to write that in here. So in here is high, and it's going outside to low. Okay, so passive transport, again, it does not require ATP. So it's just moving things from high to low. So you've got a lot out here, it's going in, or you've got the scenario where you've got a lot in the cell and it's going out, okay? This is passive. No ATP, no ATP. All right. Channel proteins. So channel proteins are going to allow things in and out. So again, this big thing here is our protein, red. Okay, so here's my big protein. It's stuck in the phospholipid bilayer. This here, this is the cell membrane. Okay, cell membrane. And the protein is basically like a tunnel that's going to allow, say, these cars, if you will, to follow that analogy, right, to go through. So they're going to go through, and again, they're going from high to low. Okay. Anytime that we have passive transport, okay, that means no energy. Things naturally are going to go from an area where there's more of them to where there's less. Okay. So on the left, there's more on the outside, so they're moving in. On the right, there's more on the inside, so they're moving out. Ion channels, again, so here's my circle, that's my cell membrane. Here's my protein channel. These are very often going to be ion channels. Okay, which means they are often going to allow through charged ions. So chloride ion might be one that maybe it's going out. Here's another one. I'm just showing you some ion channels. Hydrogen ions, maybe that one's going in. Again, it's going to be going from an area of high to low. Whenever we're talking about facilitated diffusion, it's going to depend on the concentration gradient. Now, sometimes these channels can open and close. So you might have a channel, here's a channel over here, and it's basically locked. So most of the time, say sodium, even if there's a whole bunch out here, okay, it can't go through because this is blocked. But if there's a certain signal that binds to it, or maybe a voltage change, then it's going to open up and it will allow the sodium in. Okay, so that is called a gated channel. So it's a gate, it's basically can open or close, can open and close. Whereas some other channels over here, just these specific examples might be open all the time. So some ion channels might be gated and some might be open all the time. There's also proteins that are called carrier proteins. Carrier proteins are going to allow something specific to go through. They're a lot slower than the tunnel that's always open. So a specific molecule will fit on one side. I always think it's like an airlock or an elevator with two doors. I'm not elevator. Yeah, elevator. So it goes in, the door shuts behind it, and then maybe it goes up or down a floor if it's an elevator, right? And then the other door opens if you've ever been in that scenario. And then it can come out the other side, or an airlock. But it goes in, the door closes behind it, it goes across, and then it opens. So these are a lot slower compared to the other ones, but they're easier to regulate. They can also become saturated, so they're all full, and that slows down transport. A couple other things I'll go through quickly. A uniporter, it's going to be one direction, one substance. A symporter, the protein is going to let two different types of molecules through at the same time, the same direction. And an antiporter is going to be two different molecules, but one's going one direction and one's going the other direction. So these are options. Electrochemical gradients. Here's my cell membrane. Now, if the molecules that we're talking about are ions, they're charged. So say over here on the right, these are all positive charges. So there's a whole bunch over here that's positive. That's going to lead to a voltage over here that's relatively higher compared to the voltage, say, over here. So the voltage over here might be a little bit lower. So sometimes you can create charge imbalances, and it basically is like charging a battery. Charge a battery, and then you can have that ready to go. And if you need to send a signal, you basically open it up and let that signal go. And that's how we send nervous impulses through the body. All right, that's it for this video.